5.1, we're dealing with exponential functions. Chapter 5 is all exponential logarithms. I don't think we've ever done logarithms, have we? Did we do logarithms last semester? Okay. So that's the log button. That's also the LN button. LN actually stands for natural log, but it's LN. Logith naturalist, I don't know. So we're going to evaluate exponential functions with base A. We're going to graph exponential functions. Exponential functions are in fact one-to-one. We're going to talk about base E, and E is approximately 2.71828. And we're going to use exponential functions to model and solve real life problems. Interest is calculated using exponential functions. Continuous interest is calculated using E. So there's where we are in 5.1. So far, this text has dealt mainly with algebraic functions, which include polynomial functions and rational functions. In this chapter, we're going to talk about two non-algebraic functions. The two we're going to talk about are exponential and logarithmic. Exponential and logarithmic are known as transcendental functions. The trig functions are also transcendental, but the only transcendentals we're dealing with during this section is exponential and logarithmic. So an exponential function, base A, can be written as f of x equals a to the x power. A is the base. What is x? F of x. What is x? X is our independent value, right? X is our variable. Where's the variable in this function? It's the exponent, okay? Because the variable is the exponent, that's why this is an exponential function, okay? So A has to be greater than 0, but it can't be 1, because what happens when you raise 1 to any power? 1 to any power is 1, which would make it a constant, okay? So x can be any real number. Base 1 is excluded because it yields f of x equals 1 to the x power, which is a constant function, not exponential. You evaluated a to the x for integers and rational values of x. For example, you know that 4 cubed is 64. You know that 4 to the 1/2 is, you know that 9 to the 1/2 is 3, just making sure you're not just reading the board, okay? You know that 2 to the 5th power is 2 to the 5th power is 32. 2 to the 10th power is 1024. Yeah, I know. Okay, but how do you evaluate 4 to the x power, where x is any real number? And that's where we're going to have to do that's when the logarithms are going to come in, not today. But logarithms are going to allow us to take that exponent and take it out of the exponent and move it to a number that we can actually use. So for the purpose of this text, we can think of a to the square root of 2, where square root of 2 is about 1.414, blah, 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 blah. Okay. I could approximate that. I could figure out a to the 1.4, but I could be more precise by going a to the 1.41. But I could be more precise as a to the 1.414. Does that make sense? And so I could keep adding the numbers that are the result of the square root of 2 and get an approximation of what a to the square root of 2 is. Use a calculator and evaluate each of the indicated values of x. Letter A says f of x equals 2 to the x power. X is negative 3.1. What are you going to do? Using your calculator, you would type 2 caret. Okay. I'll just stop after 3 digits. Okay. So about 1.116. How come it's not a negative number? Negative 3.1, that our x value is negative. How come our answer is not negative? Okay, what does the negative exponent do? One over 2 to the 3.1, right? So to get rid of a negative exponent, you pass it through the fraction bar. We've talked about this before. Okay. Letter B, f of x equals 2 to the negative x power. X is pi. How do you type that? Okay. And you get? Does it make sense that those two answers are pretty close to the same? Why? Okay. Yeah. 3.1, 3.14. Okay. F of x equals 0.6 to the x power, but x is 3/2. You type 0.6 caret. You can do the fraction. Okay. Be careful here. Either make sure you enter the fraction as 3 over 2, or maybe you want to do it as 1.5, or maybe you want to do it as in parentheses 3 divided by 2. Because I think if you did 0.6 to the third slash 2, it's going to take 0.6, raise it to the third power, take that answer and divide it by 2, because the calculator understands order of operations. Am I right? Okay. So when you type it in any of these ways, what do you get? If you type it like this without the parentheses, you get the same answer? Okay. I'm always reluctant about doing that with fractions, though. Oh, that's because the 3/2 is all up inside. Yeah, because it's all up inside the, yeah, of course. Yeah, the parentheses aren't needed. I'm thinking about old school calculator where it didn't actually put it in the exponent. When you push the caret on this calculator, it actually takes you up, right? So all your typing is in the exponent. On the older calculators, you would do a caret, and then whatever you typed after that would be the exponent. Yeah, it would show the caret. Okay, so with current calculators, you're good without the parentheses. Sorry about that. Questions? Okay, you want about 10 of those on the test, right?
I want all of this on the test.
Yeah,
Okay.
joke first.
So there you go.
Are we gonna have to like list our speech groups?
No.
You think
This time.
Okay. In the same coordinate plane, sketch the graph of each of the functions. I'm going to graph 2 to the x power. I'm going to graph 4 to the x power. So if we were to make a t-table of this, I have 2 to the x power. I have 4 to the x power. And let's go with some x values. -3. What's 2 to the -3rd power? Should be like 0.125. Okay. Which is 1/8. So I went back 3, 1, 2, 3, up just a little bit. What if I plugged in, and we'll come back to the other one in just a moment. I'll change colors for that graph. Let's go -2. Okay, 1/4. -2, up a little higher. Let's skip. Let's go to 0. 2 to the 0 power is 1. 0, 1. Let's skip a little bit. Let's go 2. 2 squared. So 2, 4. 2, 4. Let's go ahead and do 3, 8. So 3, 8. Okay, what's happening here? Okay, it's going up quickly, right? What about over to the left side? Okay. Okay, it's always continuing. It's always increasing. Always, always, always. Okay. Did you say it's doubling? Okay, so going this way, do y'all agree it's doubling? What about going this way? Halving. Will that ever get 0? Theoretically speaking, if I took the number 1 and cut it in half infinitely many times, I would still not be at 0. Right? Okay. So the x-axis is called what? An asymptote. Perfect. I kind of missed that point. That's not a bad graph. Let's do 4. 4 to the negative third. 1/64. 4 to the negative 2. Okay. 4 to the 0. Interesting. 4 squared. 4 cubed. Okay. This is interesting. Why? Anything raised to the 0 power is 1. Anything raised to the 0 power is 1. Okay. So plotting these points, I'm going to go ahead and plot this point here. I'll plot, let's go ahead and plot 4 to the first power. 4 to the first power would be 4. 4 to the second power would be off my graph. So this graph is below the blue one. Then it's above the blue one. Okay. So there they are graphed on the same one. Thoughts or any insights on that? What did you say, Matt? No, they both pass. It's 2 separate graphs. It's 2 separate graphs. Okay. He said it fails a horizontal line test. Well, that's because it's 2 different functions. Each function passes, correct? Okay. Okay, here they are graphed. Exactly what we did. They've got a couple more points that we didn't have. Both graphs are increasing. The graph of g of x equals 4 to the x power is increasing more rapidly than the graph of f of x equals 2 to the x power. What is 4 to the x power doing as we move to the right?
It's
Multiplying by 4, right? The other one is doubling, right? Multiplying by 2. This one's multiplying by 4, so it's going to go up a lot faster. So here are the basic characteristics of exponential function y equals a to the x and y equals a to the negative x. This is 2 separate slides. This slide is going to show a to the x, meaning x is a positive number, okay? So as long as a is greater than 1, the domain, x can be any number. The range from 0 to infinity, can it be 0? Can the range be 0? Is it a bracket or a parenthesis? It's a parenthesis because it can never get there, right? If you take the number 1 and cut it in half infinitely many times, you're still not to 0. The function is always increasing. X-axis is a horizontal asymptote. As the value of a of x approaches 0, x is approaching negative infinity. It's a single smooth curve. You can draw this graph without picking your pencil up, therefore it's continuous. So those are the basic characteristics of y equals a to the x power, where a is greater than 1. Next one. This is y is a to the negative x, a to the negative x. So when it was a to the x, oops, a to the x, it was increasing, right? A to the negative x, what's it doing? It's decreasing. Because you have that negative exponent, which causes a reciprocal. So a reciprocal of a negative number is going to be positive number. So over here, it's getting bigger as you go to the left. But as x increases, it's approaching 0. Domain is the same. Range is the same. Y-intercept is the same. On both functions, the y-intercept was 0, 1, right? Okay. When your exponent is negative, it's going to be decreasing. The x-axis is a horizontal asymptote. It's continuous. So the graph of an exponential function does one of two things. It is either always increasing or it's always decreasing. How do you tell? You look at the exponent. Questions on this? Okay. The graphs pass a horizontal line test. Therefore, the graphs are 1 to 1. You can use the following 1-to-1 property to solve simple exponential function equations. If a is greater than 0 but not 1, a of x is equal to a of y if x and y are the same. That's the 1-to-1 property. E, 2.71828. That is natural base. E is a number, folks. E is not a variable, okay? Just like pi is a number, right? Okay, so E is just a number. That's approximately 2.71828. F of x equals e to the x is called the natural exponential function. Notice that 0, 1 is on the graph, and it should be, right? Anything raised to the 0 power is 1. E to the 0 power is 1. I to the 0 power is 1. E is the constant 2.71828. X is the variable. I talked about that already. Okay. Calculate these. What is the value of e to the x for each of these values? So letter A, I'm talking about what is e to the, and on this, you don't have to push the caret button, do you? If you push that e to the x button, it puts the e on the screen and it automatically puts your exponent up there, right? So e to the negative 2 is about, give me 3 decimal places. E to the negative 1 is about, okay. E to the 0.25.
Where's the E button?
It's on the left side.
Second button.
There's the E button here, but if you go second and press this one. Okay.
That one up there.
Oh, okay.
Second natural log. And let me point that out to you too. I've talked about this before on the calculator. The on and the off button is the same button, right? Because on and off are inverse operations, right? Add and subtract are right on top of each other, aren't they? Because adding and subtracting are inverse operations. Multiply and divide, inverse operations. How about natural log of x and e to the x? It's the same button, isn't it? Because they're inverse operations. Okay, just like log x and 10 to the x. Same button, aren't they? Inverse operations. Okay. Okay, back to the question at hand. E to the 0.25. 1.284. I'm just trusting y'all. and e to the negative 0.3. 0.741. Okay. Let's get some of those on the test too.
Why are you just trusting us? Why did you do it?
The answers are right here. Okay. Any other questions about entry on those? One of the most familiar examples of exponential growth is an investment earning continuously compounded interest. You've probably heard of quarterly interest, monthly interest, annual interest, right? When you hear those terms, they're telling you how many times a year it's compounded. So monthly interest is compounded how many times a year? Because there are 12 months in a year. Quarterly interest is compounded how many times? Because there are 4 quarters in a year. Daily interest is counted how many times? 365.25 times. Just kidding. 365, not counting leap year, right? Because there are 365 days in a year. Continuously means every microsecond is being computed. In fact, even more frequently than that. Continuously compounded means it's the compounding does not stop. Okay? Probably. It's always increasing. And so do you think if you got a choice, you got $1,000, you're going to put it in a bank that pays quarterly, you got a bank that pays monthly, and a bank that pays continuously. Which one are you going to put it in? Because the amount's going to be hugely different, right? It's almost the same. Okay, the difference is almost the same, and you're going to see why as we talk through this. So the formula for compounded interest, compounded n times a year, is A, the amount after the investment, is equal to P, the amount you put in, times 1, that way you get your money back, plus a fraction. Well, that's going to be your added interest, right? Raised to the nt power. Interest rates are normally small. N is the number of times it's being compounded a year. So if the interest rate was 3%, and you're compounded monthly, it would be 0.03 divided by 12. Very small number, isn't it? Raised to the 12 times however many years there are. Okay. If it's continuously compounded, it'd be the 3% divided by basically infinity. What's 3% divided by infinity? Approximately nothing. But it's raised to the infinity power. So basically you have 1 raised to the infinity power, which is 1, right? So you're not going to see a whole lot of difference between daily compounding versus continuous compounding. Is continuous compounding going to be more? Yes, it will be. It will be. But we're talking $4 or $5. Okay. It's something. Okay. So this is number of times it's compounded per year for T years. So this is the one that we use frequently for monthly, quarterly, annually, and that kind of thing. Next slide. So we're going to develop the continuous one, and I'm just going to kind of talk y'all through this. Using exponential functions, we're going to develop the formula and show how to do continuous compounding. Suppose P, that's the amount of money that you're going to put into the account. It's invested at some interest rate. We'll call that R. We're only going to compound it once a year. If the interest is added to the principal at the end of the year, the new balance is P1, that's how much you have after 1 year, right? Is equal to the amount you started with plus the amount you started with interest. That makes sense? I could factor a P out of that and get P is 1 plus R. That kind of makes sense because 1, that guarantees you get your money back, plus means you're getting more than your money back. R is the interest rate. Y'all good with that? Let's expand this. P1 is after 1 year. Okay. If we moved on, basically, we're going to just keep doing this process. So at year 0, that's how much to start with. P is equal to P. That makes sense. P1. P1 is going to be P times 1 plus R. I just showed you where that came from. P sub 2. Well, P sub 2 is going to start with your P sub 1. And you're going to get more interest. So it's going to be P times 1 plus R squared. After the 3rd year, P times 1 plus R cubed. After the 10th year, what would it be? P times 1 plus R to the 10th. And we could go to any number we want. So P sub T, meaning I don't care how many years we're going to do this. If it's compounded once a year, the formula is going to be P times 1 plus R raised to the T power. Because you can take that principal and multiply it by 1 plus the interest over and over and over and over again. Moving on. To accommodate more frequent quarterly, monthly, daily compounding, let N be the number of compoundings per year and T is the number of years. So basically, we're going to have to divide by N, and we're going to raise that T. We're going to multiply the T by the N as well. Okay, and that's the standard formula we use for compounded interest. The formula for N compoundings per year, let M equal N over R. So we're just going to kind of make the equation just a little simpler by changing N over R to M. Okay, here's the original equation. This is the amount with N compoundings per year. If we change N over R to M, or if we solve this to get N by itself, we'd have N equals Mr. Right? So we can change the N's to MRs. That can be simplified. R over R cancels, right? So we now have 1 over M to the MRT. Raising a power to a power, you multiply the exponents, correct? When you multiply power to a power. So using that property of exponents, we can actually rewrite that to 1 plus 1 over M to the M, all to the RT. And this right here is very interesting. 1 plus 1 over M to the M power. So Molly, I want you to compute this, but I want you to do M to be 1. Okay. Matthew, I want you to compute this, but I want you to have M equals 100. Okay. Ethan, I want you to compute this, but I want M to be 10 million. Okay. Yeah, let's just stop there. Okay. No. Okay, Molly, what'd you get for 1? 2. So raising this thing to the first power, she gets 2. Is 10 million going to be a lot different? Okay. Who did the 100? What'd you get? You didn't? 1 plus 1 over 100 in parentheses raised to the 100 power? Okay. Huh? Exactly.
Like 2.7048 is the rap.
Okay. And Ethan, what'd you get for 10 million? What is this? As m gets closer and closer to infinity, what is 1 plus 1 over m raised to the m power? It's e. Okay. Which means if I take this part right here and replace it with e, I have p times e to the RT. Have y'all seen that before? Have you ever seen this formula? A equals P e to the RT. That is the continuous compounding formula. Okay, what'd you get for 100? Oh, you already told me. Never mind. What's your question? Well, what I was doing is I was expanding what this guy right here turns out to be. And this is what I was talking about a while ago. I've got 1 raised to an infinitely large number, right? And I'm adding something to that 1. But what am I adding to that 1? What happens is m gets larger and larger and larger. What am I adding to 1? A smaller and smaller number, right? This number right here is going to get closer and closer and closer to 1, right? Because 1 over m gets closer and closer and closer to 0. But it's always going to be positive. So I'm definitely adding 1 plus something raised to a huge number. 10 million is a big number. So 1 plus a very small number raised to a very, very, very large number is only 2.71828. Okay. So here's the next slide. It shows multiple entries. And they went all the way to 2 million or 10 million, just like I showed you. I just did a sampling of these. Okay. So A equals P times E to the RT. For T years, the balance A in account with principal P and annual interest rate of R is given by these formulas. So for compounding n times per year, you use this formula. For continuous compounding, you use this formula. So I would make sure those formulas are on your cheat sheet. Okay. So this one would be compounded quarterly, compounded monthly, compounded daily, compounded whatever, annually. Okay. And as soon as you see the word compounded continuously, we change the gears, go to this guy. All right, we'll go ahead and move on here. You invest $12,000 at 3%. Find the balance after 5 years. Compounded quarterly, compounded monthly, compounded continuously. Which one's going to give you the most money? Continuously. Okay. Now, folks, this is just a matter of plugging numbers in, right? What is T? Huh? 5. T is 5. What is R? 0.03. Don't miss it because of that. Okay. Interest rate is per cent, per century, per 100, right? So 3 per 100 is 0.03. Okay. So this is just plugging those numbers into 3 different formulas or 2 different formulas. And here you go. Compounded quarterly. There are 4 quarters in a year. So N is 4. T is 5. R is 0.03. After 5 years, my $12,000 becomes $13,934.21. I made $1,934.21. Next slide. Okay, this was compounded quarterly. Next one, compounded monthly. N is now 12. Everything else is the same. How much more money did I make? What was this number?
13,930 something.
Was it 930?
37, I think.
Was it 937?
It was 13,934.
934. So because it was compounded 12 times a year instead of 4 times a year, it went up $5. Okay. How about when it's compounded continuously? I'm at 13,939. 13,942. I made $3 extra over 5 years. Okay. So is it really worth it? The different rates? Okay.
Yes, one.
The interest rate is the most important number. Okay. Yeah, it's important how many times it's compounded. I get it. I get it. But the interest rate is more important. Okay. And that, folks, is the end of 5-1.
Is it going to happen? No.